Hello everybody, I welcome you all in this session, and the target of this session is basically is universe itself behaving as a natural particle accelerator. And at the same time, if I talk about the microscopic particles, say for example, nucleus is a very dense matter, and if we want to know anything about the nucleus of an atom, we certainly need high energy particles, and these high energy particles, we would like to collide them with the target nucleus. So once there is an interaction between the particle that you are hitting with the nucleus, there will be an interaction, and that interaction will result in understanding the nature of that minute particle. So it's like investigating a person. Suppose there's a person, and this person is hiding some classified information, and he's not exposing that information. So what we do in that case, we have a different means of extracting that information from that person who's hiding that classified information. So what can be done? I think interrogation is one of the ways, and you interrogate the person, and there's a probability that the person may expose the hidden information that he or she possesses in that framework. So we can correlate this example with the real target particles existing in the universe. If we want to know about a particle, say for example, we want to know about an atom, we would like to hit this atom. So hitting this atom will, once there is a hitting, a precise hitting, a precise shot may excite the electron of that atom, and while de-excitation, we have the information about that atom. We have an information about the energy that this electron possesses in that atom. Now, the atomic scale is in terms of electron volts. So we generally need very low energy particle accelerators for atoms to interrogate them, and once we interrogate them, we obtain the information about that system. Now, the point that I want to make here in this interaction, in this conversation, is that this universe, this cosmos, which is filled by billions and billions of galaxies, trillions of stars living in these galaxies, and billions dying every year, and new of the billions of the stars are born in this living, vibrant universe. Can we correlate this universe to a particle accelerator? But before I say anything about the universe, I would like to introduce you with what a particle accelerator basically means, and how we can extract the information about the minutest particles that are existing in this universe. So that's the target. So the point is that the universe is not just a stage for physics. It is itself an experiment going on. Now, this experiment is conducted by some unknown forces. That's not our point. The point is that this whole cosmos is a laboratory, and this laboratory is performing all types of experiments. And in many ways, it acts as the ultimate particle accelerator. And we can see, we would like to see that this universe is naturally acting as a particle accelerator. Far beyond what humans can build, or what humans have already built till now in the form of an accelerator at CERN, or the accelerators in the different parts of the globe. So the point is, what is a particle accelerator? So it is just a device that speeds up the particles involved close to the speed of light, and these particles can be protons, they can be electrons, they can be ions, and what we do is we try to speed up these particles to very, very high velocities, to very high speeds close to the speed of light. And we have the examples, and mostly popular particle accelerator throughout the globe is a Large Hadron Collider, and this Large Hadron Collider is at CERN, and then we have another accelerator, RHIC. Now, what is a particle accelerator? A particle accelerator is a machine that gives you the particles, and these particles accelerate, and the energy of these particles keeps on increasing, and the target is that you always try to build, always try to generate the particles who are highly energetic. So as I started with an example of nucleus in the beginning, what I said is, if you want to know anything about the nucleus, you have to interrogate this nucleus. So how can I interrogate it in a physical world? I can interrogate it by beating this nucleus. So if I beat this nucleus, it will recoil whatever the dancing the nucleus will do by hitting those probing particles. It will give me an information about itself. So that's basically the main motivation of creating, of designing these particle accelerators. And what we do, we generate the particles, and we use different laws of physics. We use different physical involvements that, by virtue of which we can enhance the speed of these particles that are emitted from a target source. So what we have in a particle accelerator, you can see this photograph is just showing, giving us a sense of a particle accelerator, where you start with some particles and you allow these particles to pass through these regions, and these regions are a source of electric and magnetic field, because you can influence the geometry of the particles by executing the magnetic field on the charged particles, and you can even enhance the velocities of these particles when they are experiencing the different magnitudes of magnetic field and different magnitudes of electric fields. And this technology is going on. Maybe it started with ordinary magnets, but now we have been using superconducting magnets, because we want particles like hadrons to accelerate, to have the velocity to close to the velocity of light, and there are a range of discovery of the new particles every time, and at the same time, if we rightly remember, the Higgs field was experimentally confirmed by performing an experiment in Large Hadron Collider and confirming the predictions of Higgs field. So this is a crude idea that what you are trying to do is you are trying to you're trying to make your interrogation more energetic. You're hitting the person with more force so that you expect that you can have more information that's embedded in that person. Now, we cannot exactly correlate the human interrogation with the interrogation of the particles that are hitting in a particle accelerator. But as a case of example, we can choose a human hiding some important information, and physically hitting can be one of the ways to obtain the information from that person. So, uh, so what we have, humans have made accelerators, and I believe Van de Graaff generator was the earliest particle accelerators that people have designed. They have invented those devices. And talking about the largest man-made accelerator, which is called as Large Hadron Collider, it has a circumference of 27 kilometers, and the energies that you can obtain, the energy of the particles that you are accelerating in these accelerators, can go up to 14 tera electron volts. But believe me, the cosmos that we have, as I started with the argument that this universe is itself, we can imagine, we can assume universe to be a particle accelerator. And if we compare the energy that we obtain in a Large Hadron Collider with the cosmos, because cosmos is naturally developing these particles in the universe, these particles accelerate beyond the limit that you have in Large Hadron Collider, which is nearly 14 tera electron volts. Okay, so what we have cosmic rays. These cosmic rays are coming to the planet Earth as well, and these are high energy particles. These are originating from the outer space. They are coming from the outer space. So that means you already have the high energy particles which we are receiving on this planet, and the energies of these particles which are coming from the outer universe, they exceed 10 to the power of 20 electron volts. So it is far, far greater than that of the energies that we produce in Large Hadron Collider. So it's millions of times higher than that of the energy of the particles that we can attain in a Large Hadron Collider. So these cosmic rays were discovered, first discovered in early 20th century by Victor Hayes using the balloon experiment. I mean, people are very well aware about this experiment, and this experiment showed that radiation intensity increases with the altitude as the balloon goes up and up, and it experiences more and more radiation. And this experiment confirmed the cosmic rays that are coming from the outer space to the planet Earth. So certainly they must have origins where from these particles are coming. So these are accelerated particles, which are coming towards the planet Earth. And talking about sources, as I said, the sources can be many. It can be a supernova, an explosion of a dying star, where you have tremendous amount of energy coming out. So a supernova, an explosion in the space, is giving the billions and trillions of particles. So the supernova, the shot of a supernova, is equivalent to a particle accelerator. It's producing the particles which can accelerate, and their speeds can go close to the speed of light. Black holes, we have Hawking radiations, because black holes, they also discharge, and these black holes can also be the sources of these high energy particles that we discover. We have active galactic nuclei that are present there, and gamma ray bursts that are happening in vicinity of the black holes. So the sources of these cosmic rays can be traced back to these important events that are happening day to day in the observable universe, where you have a supernova consistently taking place in different galaxies in this universe. So once you have a supernova explosion, what it does basically, it produces the shock waves from the stellar explosion. And once you have the shock waves, it produces the particles, and these particles accelerate, and the particles that accelerate, they can be protons, they can be heavier nuclei, to very, very large energies. Pulsars and magnetars. So these are the objects that are living in the observable universe. They are also the sources of these particles. So they are also these Big Bang shots that produce these high energy particles. So talking about a neutron star becomes, we call it a pulsar if it is spinning very fast. So a rapidly spinning neutron star with intense magnetic field. What it does, it generates the particles to very, very large energies. Magnetic accelerations, since these pulsars, their magnetic field consistently keep on changing, that creates the beams of high energy particles. If you rightly go back to that particle accelerator as I showed you, I told you that you can influence the motion of the charged particle by varying the electric and magnetic field. So in nature, you have huge magnets, and the magnetic field that's changing there is extremely, you cannot replicate a pulsar in a laboratory on the planet Earth. So universe is creating tremendous particles with having tremendous energies. Black holes, we have supermassive black holes with accretion disks. And what does these accretion disks, the region surrounding those black holes, they can accelerate the matter to near light speeds. So if you have the charged particles in the vicinity of these disks, they can cause the jets, and these jets can accelerate the matter to near the speed of light. Now, at the center of the galaxies, what we have supermassive black holes. Even we don't understand that how these black holes have come to life. There's no explanation for these massive black holes, even at the center of the Milky Way. So what's happening is that these supermassive black holes, they eject relativistic jets, as in the case of black holes I was talking about, and then accelerates the particles close to the speed of light. Gamma ray bursts, and what you consistently can have extremely energetic explosions in the distant galaxies, and these extremely energetic explosions that happen in galaxies, they are thought to be one of the most powerful natural accelerators. They accelerate the matter, maybe they ionize the matter that is surrounding them, ionize them and then accelerate them, and we have those particles of energies of the order of 10 to the power of 20 electron volts. Now, talking about Fermi acceleration, this is a process by which a charged particle gains energy through repeated scattering by the magnetic field. So this can be an explanation as to the previous slide when I was talking about the pulsars, because pulsars are rotating neutron stars, and their spinning motion gives the birth to the magnetic field. So the magnetic field that's produced by these pulsars, that gives the energy to the matter that is in vicinity of these stellar objects. So what's happening here is that this Fermi acceleration is a process that's linked with with those pulsars, and it's a process by which these charged particles, what they do, they gain the energy because the magnetic field surrounding those pulsars, it keeps on changing so fast. So it gives birth to the shock waves, and these shock waves can transport the particles to very, very large distances. And the universe itself has the magnetic field. So we have intergalactic, interstellar magnetic fields acting as cosmic accelerators for the charged particles. So that means if we think about the galaxy, the galaxy overall has a magnetic field. It has a giant magnetic field. So where those magnetic fields are changing, they are consistently giving birth to the highly energetic particles. And a fraction of those particles we receive on the planet, whom we call as cosmic rays. And what we have, ultra high energy cosmic rays. These are observed energies of the order of 10 to the power of 20 electron volts, and if you correlate it, it is equivalent to a baseball, this energy thrown at 90 km per hour and compressed into a single photon. And this is how you can correlate this energy of the particle, the energy of the order of 10 to the power of 20 electron volts. Now, the point is, so whatever is happening in the universe is happening fast, it's happening with different sources. You don't have a single source of radiation that's coming on in the observable universe. And this observable universe is filled with these sharks producing the highly energetic particles. So first of all, we can assume that this whole universe is a huge particle accelerator. The Milky Way itself is a huge particle accelerator. The Andromeda galaxy is a huge particle accelerator. We constantly have highly energetic particles coming from these sources. So we have the atmosphere. This atmosphere blocks most of the cosmic rays. So if there is no atmosphere, so our existence is not possible on this planet. So we are shielded by the atmosphere surrounding the planet. So one way it's a disadvantage for us because we cannot detect all the particles that are coming from the outer universe, because most of these cosmic ray particles are blocked by the atmosphere. So what we do, we detect them through air showers, and we detect them through the detectors, what we call as Kern-Coe detectors. Now, talking about a famous experiment that was held in Pear Order Observatory, an ice cube neutrino detector. We have telescope arrays, now all studying high energy cosmic particles that we receive on the planet Earth. So there are many experiments going on. So what is more important here is to have a detector, because you already have a particle accelerator at a very colossal scale, and your job is to detect it. Your job is to see the particles that are coming from the outer universe and look for their origins. Now, if I compare the accelerators that are made by man with the accelerator that's there by virtue of the Creator, there is a huge difference. So in LHC you have up to the 14 tera-electron volt energetic particles coming on, but in the nature you have cosmic rays, and their energy is of the order of 10 to the power of 20 electron volts, 70 million times more powerful than that of a particle accelerator that we have at CERN. So the universe provides energies unreachable by current or even future human technologies. There is tremendous out there. There are tremendous accelerators out there, and the technology that we possess, maybe that's not enough to detect that all and look for the all things that are coming. So it's all physics. So physics, what physics does, it helps us to study these fundamental forces, test the relativity, and explore the quantum gravity regimes of this natural particle accelerator producing these highly energetic particles. So these cosmic accelerators, they are basically the laboratories for us, and these are natural accelerators. They give us insight into the conditions impossible to replicate on the Earth. You cannot replicate the energetic particles that are coming from a pulsar, because you cannot have a pulsar kind of thing on the planet. So that's what I'm trying to say. Anything is possible. You can't have the science is open for all those impossibilities that are existing in the universe. But up to now, it seems that it's impossible. So there is obviously a philosophical angle, and the universe itself becomes not only the subject but also the instrument of the science. The way what we do is we perform an experiment in the laboratory. We have to have the instruments for a particular purpose that we want to calculate in the laboratory. So you have a laboratory, and you try to create all the laboratory conditions for your experiment. And then you perform an experiment and look for the results. But at the same time, the universe itself is a laboratory, and it's an instrument of science. And we as humans have to influence those points of science that can lead us to understand more and more about the nature of reality. So next generation detectors will help us trace sources of cosmic rays more precisely. So people are going on developing more and more sensitive detectors, so that we can have more and more understanding about these cosmic rays, the particles that are created by the accelerators present in this universe. Now, there are questions. Now, why do the highest energy cosmic ray come from? This is an open question. We don't know exactly where from the highest possible energetic particles are coming, and what physical processes sustain such accelerations over millions of the light years that these particles travel. So these are the open questions, and we should all look for answering those questions, and we should look for more and more science to answer those questions. So to conclude this talk, I should say, because I started with the question that can we assume that universe itself is a particle accelerator? The answer to this question is yes. The universe is the greatest particle accelerator, and which man can never build like. Now, but you cannot say can never. For humans, there's a favor, they may do it someday. Now, it dwarfs all the human machines. So all the machines that the mankind have designed, and opens doors to the new physics. So this is the conclusion, and I would not like to do this. So I hope you like this. You like this video. If you like this video, I request you to subscribe to the channel. I request you to like the video as well. So goodbye.